Hi, this is Paranormal Girl. I've talked about the Mars rover landing and I've also spoken about the moon landings. So let's now take a scientific look at the Van Allen belt and space radiation challenges. The bird radiation detector report seemingly confirms the dosimetry radiation data for the manned Apollo lunar flights was collected while remaining in low Earth orbit. The December 2014 Orion test flight was flown in preparation for manned explorations to the Moon and to Mars, with the trajectory designed principally to examine the heat shield performance at re-entry. Orion had to make a high elliptical orbit, taking it some 3,600 miles, which was 5,800 kilometers, off the surface of the planet into the region of the lower or inner Van Allen belt. As a result, even though Orion's apogee was well shy of the worst part of this inner belt, another 2,344 miles further out, Orion carried instrumentation for registering the radiation environment in the given advanced electrical systems that the Orion craft would be using, and that the future astronaut occupants. This test made engineering sense, yet it didn't feature very much in the pre-flight literature. If the NASA Orion blog for November 2014 carried a vague mention of this particular test, it was also managed to convey the notion that radiation would only manifest at the moment of re-entry. Let's see if I can blow this up a little. So here's a diagram of the exploration flight test 1. You can clearly see through all the pointers here how this made sense. This is the overview. Although Orion will not carry any people on its flight test, it's designed for astronauts, and engineers want to find out what conditions will be like inside the cabin as Orion travels through high radiation and extreme temperatures during this test flight. The very colourful NASA Orion press kit doesn't refer to radiation data acquisition at all, nor was it listed among the flight objectives of a 2014 test. Perhaps the press kit was the first ordinary media, as the specialist website Spaceflight 101 did mention this aspect of the Orion test. In this elliptical orbit, Orion will have to pass through Earth's radiation belt. The radiation inside the crew module will be measured to evaluate shielding materials that will protect future crews in the harsh radiation environment of deep space. This statement ignores basic punctuation and technical accuracy. First, Orion did not pass through the belt. It merely skimmed the edge of the lower belt. Secondly, it infers the radiation in deep space and is harsher and somewhat different. From what? Shallow space? Softer space? Interestingly, at one point in the Orion radiation report, just after the instrumentation had registered a spike in the extremely potent area of the inner belt, and radiation is described as softening. Upon entering the trap belts, a region of high absorbed doses rates was encountered, followed by local minimum caused by a softening of the trapped proton energy spectrum. These might be technical terms used by the experts, but when presented to the general public, there is the potential for manipulation of reality through vocabulary. The dividing of space is cislunar space, the region of space within the orbit of the moon, and deep space beyond lunar orbit. It lulls the public into false assumptions concerning the safety of manned space flight and has little to do with the reality of the space environment. NASA documents that adapt these terms while explaining that deep space missions are more dangerous for astronauts than cislunar or near-Earth expeditions are merely stating the obvious. Clearly, the longer one is out in space, the higher the probability of encountering problems of ionizing radiation over and above the extant background levels. If Curiosity outward bound radiation data acquisition has aptly made that point, it also doesn't take a genius to understand the accumulated or total dose received by an astronaut over time is going to be more for a longer trip and will only be mitigated by the quality of protective shielding provided. However, this division of space into separate zones does not mean in terms of time and distance that travel to a location comparatively near to Earth, such as the Moon, or one of its Lagrange points, is less risky. Yet, this is the notion that NASA would prefer everyone to accept, stating that the Moon is only a few days away. Mars is 15 months away in some scenarios. If NASA uses this language, it's hardly surprising that others repeat it. And here are a few diagrams that mention cosmic radiation levels. I'll leave the link in the description for anyone who wishes to have a look at this. This is another diagram of radiation exposure and how it compares. The first one here is, of course, Chernobyl. The worst of times. In 1966, 3 years after starting work on 2001: A Space Odyssey, fully aware of all the issues involved with manned space flight, Arthur C. Clarke noted that the Apollo manned space flights would be getting underway at the very worst time of the solar cycle. He noted that astronauts would be traveling under the worst possible conditions should solar activity occur. The astronauts would start to die of radiation problems in a few hours, offering the politically useless recommendation for Apollo that generally speaking the astronauts only travel at solar minimum, and the physically useless recommendation if the Moon was the destination. The astronauts should stay within the Earth's atmosphere at times of solar events, Clarke added. A careful watch for solar flares will always give us a day's warning of an approaching storm, and this will be no handicap for lunar travel, for flights to the Moon will last no longer than this. Clarke ostensibly ignores the fact that it was calculated that to reach the Moon in an Apollo CSM it would take around 4 days, and that the Moon is totally unprotected from space radiation. By 1970, Clarke had modified his opinion. A few hours flight time away from Earth, one can only come home in a hurry. Yes, Arthur, if in Leo and not on the way to the Moon, given the limitations of rocketry and orbital mechanics, when it comes to a lunar mission, this was, and still is, inaccurate. Such fallacies uttered by celebrity experts are accepted by the general public as scientific truths. In 1993, NASA's Space Radiation Analysis Group, SRAG, had this to say about the Apollo missions and solar activity. Between Apollo 16 and 17 missions, one of the largest solar proton events ever recorded occurred, and it produced radiation levels of sufficient energy for the astronauts outside of Earth's magnetosphere to absorb lethal doses within 10 hours after the start of the event. It is indeed fortunate that the timing of this event did not coincide with one of the Apollo missions. Accurate prediction of solar particle events still is not possible. In addition, the biological effects from long-term exposure of high-energy galactic cosmic radiation is not well understood. We are no better off. Back in 2014, the SRAG website was last updated and reviewed that year and hosted a page explaining the considerable resources invested in around-the-clock monitoring of the sun's activities, something of great importance for those on the ISS. While another page on the same SRAG site states that the solar particle events, of which solar flares are a part of, particular concern to astronauts, and that the SPEs are impossible to predict in advance. Notwithstanding the good fortune enjoyed by Apollo, it's time to put a stop to the myth that everyone is mostly safe from radiation hazards in Leo and somewhat unsafe from Leo out to the moon, and terribly unsafe beyond lunar orbit to Mars, Venus, or elsewhere. When it comes to ionizing radiation, the problems for a human potentially start to build as soon as the astronaut leaves the Earth's atmosphere. Here's another diagram showing not bullet points, but actual points of what they're actually describing here in this document. With Orion's current technical configuration, the final architecture of the shielding, should it ever get to the point of going somewhere other than high Leo, will have to be a trade-off between the amount of risk NASA considers acceptable for the crew and its ability to launch the resultant spacecraft into the desired trajectory. The other beltway. Taking all the above into consideration, it's not surprising that the study of the Van Allen belts was ongoing since the late 50s. Continuously astonishes us. Having been attacked from below by human beings during various nuclear tests, among which US operations Argus and Starfish Prime, the belts have also revealed themselves to be far more unpredictable than expected, showing a variation in responses to apparently similar solar events impinging upon the region. In early September of 2012, a few days after the launch of NASA's two Van Allen probes, the REPT, Relativistic Electron and Proton Telescope experiment, recorded the existence of a third belt which not only affected the inner regions but also extended the outer belt much farther into space than usual. This situation lasted 4 weeks before restoring to normal, and scientists seriously considered that textbook asserting that VABs considered the two distinct zones of trapped, highly energetic charged particles, chiefly protons in the inner lower belt and electrons in the outer upper belt, would have to be rewritten. The University of Colorado, Daniel Baker, principal investigator of the REPT and first author of the science paper published on the 28th of February 2013, made a really useful comparison between the VABs and the particle storage rings in a particle physics accelerator. He states, in accelerators, magnetic fields are used to hold the particles orbiting in a circle, while energy waves are used to buffet the particles up to ever faster speeds. In such accelerators, everything must be carefully tuned to the size and shape of that ring and the characteristics of those particles. The Van Allen belts depend on similar fine-tuning. Given that scientists see the rings only in certain places and at certain times, they can narrow down just which particles and waves must be causing that geometry. Every new set of observations helps narrow the field even further. With the potential for the wide variability of the VAB's activity at any given time, It clearly makes sense to monitor the VABs at every opportunity, and it's entirely understandable that the organisers of the Orion test would want to run yet more evaluations of the conditions to which the Orion astronauts would be subjected, in the lower portion of the belts at least, because in terms of distance from the apogee of the Orion flight, the belts continue for another 6.5 radii before the energy from the outer belt normally declines. Here's another diagram that would explain that. This is a 1958 section of the Van Allen belt with the maximum distance of the Orion EFT-1 test from the surface of the Earth. A case of simple avoidance. Just why such monitoring should then be considered an unmentionable item for the Orion flight objectives is rather a mystery, as in the fact that when the technical report for Orion EFT-1 were published on NASA's technical report server, it included an incorrectly titled PDF document on the engineering undertaken for the protection against the radiation for the guidance, navigation and control GN&C components of the spacecraft. But the radiation data acquired by Orion relative to the interior of the craft and its future human occupants was not immediately apparent. As it turned out, for that data to be available, the FOIA, US Federation of Information Act, request was required. That was a saga in itself and best told by the participant, who kindly sent a copy in September 2015. The report was dated 1st of June 2015, and it mentioned a reference for accessing the unclassified document with unlimited distribution that the very NASA technical report website, where it was only remarkable by its absence. However, some weeks later this report was posted by another NASA site under a completely different electronic title. The manifest disinclination in place the results of these findings in the public domain implies that the radiation data obtained during the Orion test was of greater significance than indicated by NASA's casual attitude during the run-up to the test. It also implies that the results would be of such importance that it was necessary to keep any mention of radiation out of the press kit, and in NASA's own Orion blog, categorize the radiation research as a byproduct of the heat shield testing. Or it could be interpreted as a whistleblow from inside NASA. After all, there was no need to stipulate the FOIA request for unclassified material which is going to be released into the public domain, yet releasing it in a way which could only be sourced, unless one knew the relevant electronic title, fulfilled the obligation to publish without actually making it readily available, until the new link was made known to the interested parties, although not necessarily all NASA enthusiasts. The old joke about the NASA acronym standing never a straight answer certainly applies to these convoluted deeds as it does to the concepts of this report that I'm reading out to you now. Mystery writers. Obfuscation when describing its principal results. It doesn't read like the usual NASA technical report, but as if written by the benefit of civilians outside NASA. Comprising input from authors representing 3 Houston-based organizations: Lockheed Martin, Information Systems and Global Solutions, the University of Houston and NASA Johnston Space Center, which finally posted it on the web. It had the snappy title, Battery Operated Independent Radiation Detector Data Report from Exploration Flight Test 1. The title reveals once again the NASA preference for symbolic acronyms over scientific brevity. For this, Orion radiation package then becomes BIRD. BIRD is the USAF slang for flying machines. Moreover, this acronym also fits the starry Egyptian symbolism preferred by NASA and which infuses the Orion program. It's a moot point as to whether this particular bird refers to the solar Bennu bird, often associated with the pyramid builders, but as far as radiation goes, that would be a neat fit. As I begin to wonder if that was another mythological solar god Apollo, had anything to do with the coyness of NASA, because according to the historical record, the only manned flights that have experienced space beyond Leo are the Apollo missions, of which over and above Arthur C. Clarke's previous comments had in 1993 had to say on this. Apollo missions were fortunate to avoid random solar proton events through short mission duration. Further missions will involve longer stays, making simple avoidance less practical. One wonders how simple avoidance can actually work when flying a fixed orbit to the moon over a period of, say, 8 days for Apollo 11. From this statement, the secret recipe for Apollo success apparently consisted of a large dollop of good fortune and a smidge of shielding, allied with a quick dash of anything from 6 to 12.5 days, and served with a source of totally unpredictable solar activity. Unless, of course, simple avoidance means very simply not leaving Earth's magnetosphere at all, not according to NASA, for again the agency assures us that Apollo is the exception to this rule. Except for the Apollo missions to the moon, NASA's manned spaceflight missions have taken place within the cocoon of the Earth's magnetosphere. As NASA ponders the feasibility of sending manned spaceflight missions back to the moon or to other planets, radiation protection for crew members remains one of the key technological issues which must be resolved. Which clearly implies that this issue had not been resolved for the Apollo program. In the light of all of this, it was worth checking the Orion radiation results to see if there were any data relevant to the Apollo within its pages, with which might explain the reluctance of NASA to post its findings. It was astonished to find that in relation to evaluating radiation problems outside the magnetosphere for future lunar and Martian missions, Apollo was simply ignored. And in another section of the SRAG documentation of 2012 on radiation measures to be taken relative to human spaceflight, we are informed that NASA has a history of radiation risk management. From Apollo, Shuttle and ISS, radiation monitoring requirements from the ISS and Shuttle had been incorporated into planning the Constellation program. Orion is what remains the reduced budget Constellation program, and during its next unmanned flight test penciled in for back in 2018, it was scheduled to fly around the moon. Yet, even the data from Apollo 8, the most comparable of the Apollo missions to Orion, the CSM around the moon flight has been deemed totally irrelevant. Granted, the shielding architecture of Apollo CSM was not in the same league as that of the Shuttle, the ISS and Orion, which might make the Apollo data a little value to engineering decisions made for the final Orion MPCV shielding materials. But given the unique status of Apollo relative to manned spaceflight, it's a little difficult to understand why the Apollo dosimetry radiation measurements would not be evaluated along with the Shuttle and the ISS dosimeter readings, unless the Apollo dosimetry data are in some way not representative of the effects of radiation on humans and therefore irrelevant as far as the Orion EFT1 goes. The Phantom Skull. With the Space Shuttle now defunct, NASA chose to compare Orion's bird data with the current situation on the ISS. Yet radiation research on the human bioorganism has been quietly undertaken on the shuttle, often on classified Department of Defense (DoD) missions. So before dismissing the shuttle entirely, and to put the low Earth orbit LEO environment into context, some previous research into radiation undertaken by shuttle crews is worth mentioning. Firstly, in this description of shuttle flight Columbia STS-28, the 57-degree high inclination orbit published by NASA's SRAG Sightful is quite helpful. The galactic cosmic ray GCR component varies cyclically with maximums at the extreme northern or southern portion of the orbital track. Minimums correspond to transit of the geomagnetic equator, with the spacecraft experiencing the maximum geomagnetic protection from GCR. As periodic intervals, large spikes in the exposure rates are encountered which correspond to passages through the South Atlantic Anomaly, SAA for short. The largest spikes are passages through the regions of peak SAA intensity, and smaller peaks represent passages through the fringes of the SAA. The unique features of this should read data are the effects of a solar particle event measured in LEO. Peaks in the DOS rate attributed to the solar particle event SPE occur at the extreme northern or southern portions of the orbital track, whereas the GCR and the SAA components shown in the figure are typical for high inclination flights. The effects of SPEs on dose rates will depend on the variety of parameters. This 8 to 13 August 1989 flight, the first since the Challenger disaster, took place under a curtain of secrecy since it was carrying DoD equipment. NASA spokesman Brian Welch was terse as to the flight details. No data other than the 57-degree high inclination to the equator of its orbit was then available. Kept just as a secret as the DoD mission was in fact that Columbia carried 11-pound female human skull, donated for science. This skull phantom, as it's known by the medical supply trade, was going to contribute to NASA radiation research. As apart from launching DoD material, Columbia was going to evaluate the penetration of radiation in the cranium as a primary component of the in-flight radiation dose distribution equipment. This skull was slightly reconfigured. The $1,500 skull had been sliced into sections an inch thick, so medical researchers at the Johnson Space Center could install more than 100 radiation detectors. Then it's been reassembled and covered with plastic that was affected by radiation, much like a human skin. The prepared skull was then put inside a locker at the shuttle's mid-deck and monitored on a daily basis by the crew. This is not where the crew member would generally stow themselves. Would not this locker provide extra shielding and potentially falsify the readings? Astronauts became exposed to more radiation at higher inclinations, so the skull would fly again in the mid-deck locker on Atlantis STS-36 in February 1990 at a 62-degree inclination orbit. And as its radiation levels also change with the altitude as well as inclination, the skull was placed in the mid-deck locker at Discovery STS-31 in April of 1990. And flew to its highest altitude at 380 miles. During the Hubble launch, at which time news of the skull's presence on its maiden flight on Columbia STS-28 broke in Aviation Week. The results of the research did not even, though the skull and the STS-28 experienced large SPE event that day before the mission ended. And here's a diagram here of the dose rate. I will leave in the description. Low inclination, high altitude flights during solar minimum produce higher dose rates than those with high inclination. Low altitude flights during solar maximum. At higher altitudes, the area of the South Atlantic anomaly is larger and the concentration of protons is higher. Although trajectories of high inclination flight pass through the regions of maximum intensities within the South Atlantic anomaly, less time is spent there than for low inclination flights. And crews on high inclination flights typically receive less net exposure to trap radiation for the same altitude. Here is another diagram of the Orion flight test. Time Bandit. From launch to splashdown, Orion flew for 4.5 hours and the ISS TEPC radiation detectors were assessed during the exact same period against the data from Orion's detectors. The ISS TEPC is the station's tissue equivalent proportional counter, and it's important for any flight above the altitude of 381.4 kilometers, which is 237 miles. Readings between the lines of NASA publications, it turns out that these instruments are themselves vulnerable to the space environment, and although upgraded whenever possible, the instruments still fail on a fairly regular basis. Although the bird graphs were published as a report starts some 2 minutes after the launch and go through to splashdown 4.5 hours later, in reality, for the first 11 minutes, bird was travelling within Earth's atmosphere, and later, after entry interface, it took Orion another 10 minutes to splashdown. So while NASA uses the full 270 minutes when comparing the Orion's cumulative absorbed dose findings at the ISS, strictly speaking, a period of 249 minutes for Orion would be more realistic. The shorter period of time set against the ISS, 270 minutes, would only make matters worse in terms of findings. That might be another reason why this data was initially hard to find, because for anyone attempting to get into space with humans in the foreseeable future, these figures are by no means encouraging. The bird reports it's fairly technical and interested reader can help themselves to contain via the link. Here the summary of the findings from the radiation detectors on ISS and Orion can simply be explained. They begin with an interesting point of view. The EFT-1 mission presented the first opportunity to take radiation measurements on the Orion MPCV. The bird acquired radiation data that are vital for understanding the impacts of transient trap belt radiation exposures on crew, health and safety for future crewed exploration missions. It might be the first opportunity for Orion, but it was not the first opportunity to understand the impacts of the VABs on the human beings. The document consists using the belts incorrectly. Notwithstanding the Apollo issue, every probe to Mars has provided opportunities to do the same. The bird data provided a preview of the radiation environment that the crew will encounter while transiting the trap radiation belts on future exploration missions. And I'll leave some more diagrams here. It would be more accurate to say that the bird data provided a contemporary assessment rather than a preview, but would recall Apollo in the minds of the public. In other words, they're lying. Here's another diagram here to have a little look at. The fact that the Apollo data is out of sync with the ISS and Orion might explain why it's totally ignored by the industry today. It would also explain the problems surrounding the Byrd report. Most especially since better methods of evaluating radiation effects on astronauts have only made things worse. The amount of radiation tolerated by a human being varies considerably, and the effects of radiation on the human organism are still at the early stages of understanding. However, results from the 2006 study indicates that protons from the cosmic radiation may cause twice as much serious damage to DNA as previously expected, exposing astronauts to greater risk of cancer and other diseases. Yet the high-dose radiation is only now being taken into account through better measurements, and a longer experience of human beings in space has always existed and had to be endured by all machines and bioorganisms traveling through it. Here's a diagram to a journey to Mars. So the conclusion. This presentation of the Orion Byrd data, together with the difficulties over its publication, infers that some within the space agency have noticed that the Apollo radiation data doesn't fit the template. Therefore, it's become necessary for NASA staff to spend hours writing statements full of observations in the literacy exercise of simple avoidance. In other words, they've lied yet again. But no amount of careful messaging of descriptions of the space environment through crafted vocabulary and pretty pictures can hide the truth contained in the actual figures. This Byrd radiation detector report seemingly confirms that the dosimetry radiation data for the manned Apollo lunar flights was collected while remaining in LEO, whether deliberately or unwittingly. NASA's own data has blown apart the notion that a manned Apollo crew ever travelled to the moon. So I will leave this link in the description. Basically, it's saying through the Van Allen belt, no one can survive. They might be lucky enough to go through the belt, but then they have to come back through the belt. Given that all this radiation is very dangerous on the human body, and these astronauts have lived to a very ripe old age, well into their 80s, makes you wonder if they actually did leave Earth at all. Leave your thoughts and comments in the section below. I'd be very interested in your thoughts on this. Again, it makes for a very good debate. Thank you for listening.